apologize for not being able to make it to the conference this week. Unfortunately, I had some visa issues, but Hello everyone, my name is Adam Carberry and I am an assistant professor of engineering at Arizona State University in the United States. I apologize for not being able to make it to the conference this week. Unfortunately, I had some visa issues, but I'm hoping that this video will at least spark some conversation and lead you down some paths of thinking about implementing engineering education in and out of schools. And why would we want to do this? How do we do this? And what is the true benefit of doing such things? Before I go into the content and the main crux of my presentation, I just want to introduce myself a little bit further. As I said, I'm currently an assistant professor at Arizona State. Prior to that, I earned my PhD in engineering education at Tufts University, where I worked at the Center for Engineering Education and Outreach under Chris Rogers. And there I really gained my passion for engineering education. I learned the importance of providing students, especially in engineering, an opportunity to do some hands-on learning that involved projects. And these projects weren't just trying to get a ball from point A to point B, but giving students projects that had real meaning, possibly even real clients, to allow students to understand and develop a personally meaningful component to the project. So it was something that they invested themselves in. I realized through this experience at the CEO that it's not just about preparing and recruiting more students into the field of engineering. The general public should have a better understanding of what engineering is. And so helping individuals develop that general technological literacy is just as important as helping students prepare themselves to become future engineers. We, of course, also want to try to stimulate creativity, pique curiosity, and build confidence so that students, as they proceed through their earlier years of education, aren't coming into that point where they're deciding what their career may be and saying, yeah, engineering is really not for me, because they're scared of math and science. And what I hope to establish in this talk is that engineering isn't just about being good at math and science. There are a lot of other components that students should realize how important engineering is to the world beyond developing the next great technology. So the first thing that I want to talk about is my experience working with K-12 teachers, teachers that are working with youth, ages 5 up to about 16 to 18 years old. And so a program that I was involved in while a graduate student, and I continue to pursue these efforts, is to work with teachers to help them develop the knowledge, both pedagogical knowledge and content knowledge of engineering. And so we have a major challenge, and one thing that's occurring in the United States is that more and more schools are starting to remove physics as a high school subject because there just aren't enough teachers who are qualified and who have that background understanding in order to teach these subjects. And so we're going to be faced with the same issues with engineering. So how do we remedy that without having to force pre-service teachers into learning all about and obtaining even an engineering degree? And so a program I was involved in was called the Student Teacher Outreach Mentorship Program. And the goal of this program was to bring undergraduate engineering students, as well as some graduate students, into the classroom to work with teachers to help develop their understanding in a real setting in a classroom. And so what we've done here is we've brought students who have engineering content understanding into a classroom to be content experts, and they're combining themselves with a teacher who has the expertise of how to teach and how to manage a classroom. What ends up happening here is that a two-way mentorship is created where the teacher is educating the engineering student on how to appropriately teach things, while the engineering student is slowly teaching the teacher a little bit about the content itself. And so we view this as sort of a three-phase model where it starts out where the engineering student who has had experience teaching before will come into a brand new teacher's class and teach the class. So the teacher is almost a student themselves. Then they move into the second phase where the teacher and the student, the engineering student, become sort of co-teachers, working together, using each other's expertise and continuing to develop their skills. Finally, we get to the point where the teacher is the one leading the discussion and the engineering expert student is really there just to be another set of hands. And of course, that being very, very important in the types of activities that we teach with engineering being very hands-on, especially when you're using Lego products. So what we've developed here through this program is an opportunity for teachers to have someone in their classroom regularly, even if it's just once a week, that they can rely on. What we've seen is that this assists teachers in maintaining an idea that they want to embed into the classroom with support. And that's the key component, is with support. All too often, we have opportunities for teachers to learn something new. They get very excited about that new opportunity and that new intervention that they may want to bring to the class. They may even try and bring it into the class, but when faced with problems that may arise, which always happen, if they don't have that support to continually develop the project and develop their own understanding, oftentimes those new interventions that could be very successful end up in the closet, not being used. So this was a really beneficial opportunity for me. I was involved both as a mentor myself and then managing and training those undergraduate engineering students to be ready to enter back into their K-12 classes that they hadn't been in themselves since being students. So that was a really interesting opportunity for me, and something that I would suggest. It doesn't necessarily mean you need to use university students, but it's all about having someone with some content expert there to support, provide that support. And so we've seen other versions of this program where local industry individuals have come in, retirees come in, and people who can just help with that knowledge. The second story / example that I want to talk about is the use of engineering informal learning opportunities for students. So these opportunities that are outside of classroom, and how can they be used and leveraged to impact what happens in the classroom? And so one of the things that I have become very passionate about when I do these informal out of classroom, whether they're in the summer or during the school year, after school programs, is that I try as much as I can to avoid having the projects that students do be competitions. And so that goes against a lot of what some of the available opportunities are for students. But what I have found is that competition is great. I'm a competitive person myself, and I play a lot of sports. But when it gets down to the nitty-gritty of wanting students to actually learn something, it's better to set a level for everyone to achieve, and have everyone achieve that level, and everyone leaves saying they have had success, versus saying whoever gets the highest or whoever gets the farthest wins. And in that case, only one student or one group of students can win. And that note that I brought up before about helping to build students' confidence in their ability to apply and learn math and science, if they just lost, they feel like they have failed. And what we want to establish, especially in engineering, because the way the engineering design process happens, you're going to fail often. And it's better to fail often and early and often than to think that you've failed completely at the end and then realize or develop this internal belief that you're just not good at this, which could be completely false. Perhaps you have reached a certain level that was quite impressive. It was just happened that someone got higher. It doesn't mean you were a failure. So what I do in these camps, and I've run a number of camps all around the world, recently at Arizona State, but in places like China and all over the US, And so what I try to do is always, especially for the boys, the male students, make sure that I set a reasonable goal for all teams to be able to achieve. Of course, if they are able to achieve it rapidly or with with ease, I always add some additional challenges, but I never change the level, making sure that I ensure that all students by the end of the camp will be successful in what it is that we were trying to do. So typically I do use the Lego product. I've been using the NXTs and I've recently switched over to the EV3s. And some of these challenges involve having students build animals and having them build robots that are not allowed to use wheels, spinning wheels, in order to make their robot animal move. And so the goal of this project isn't to see who can get it to go the fastest or who can get it to move the most, but it's to see if you can program an animal to search for food, which is represented by pieces of tape, and they use their sensors within their kits. And then if they don't find the food, to make some sort of negative sound, like they're crying because they didn't find the food, or if they do find the food, to make some sort of joyous sound. And so what you end up having for the final presentation when the parents come is a robot zoo, not a who got their car to go the farthest. And this is always very exciting because the students become very passionate about their animal. And when you have students build a zoo, they all want to make different types of animals. And so you rarely have multiple groups of students building the same animal. So again, you're eliminating the ability for students to compare against one another. If one student builds a penguin and another student builds a bear, it's great. They both were able to build an animal. And it's all part of our one happy zoo. And so what this is doing is it's making it a positive experience for the students because ultimately they all tend to have success, different levels of success, but they tend to have something that's moving and something that does excite the crowd when you present these to the parents or to whoever may be at that presentation. But you're giving those students some confidence in their ability to do to whatever level they were able to accomplish. And this is helping to build that confidence. It's also piquing that curiosity of, well, what more could I do? What else would have done, maybe with a different animal, things like that. So I'm just trying to get students excited. These camps I typically run with students from around age 7 to probably around age 13 or 14 years old. So beyond that informal teaching is what I'm currently actually doing in my classes. And I think a lot of what I'm going to talk about, even though I teach it at the university level, are things that could be applied at much younger ages. And it's just a matter of making sure that you frame the task in a way that challenges that particular age group. What I currently do in my second year project class for university students is I give them 2 Lego challenges as part of the overall class, and I include a final project that I'll talk about in a second. The first task is a typical maze task, but I don't do the here's one path through the maze and everyone has to find their way through the maze. What I do is I set it up so that there are 3 starting locations, and I ask students to write one single program. So they're only allowed to write one program, and I challenge them. I have them program in LabVIEW so that they are at least experiencing a software that is applicable for their possible careers. And I have the students write this one program, and they have to develop a strategy of how they are going to write a single program for the robot that they build to escape this maze. In addition to not only having them do programming and, of course, building with the robot, is I have the students do some statistical analysis on their robot's ability to escape the maze and things that they may or may not be able to improve upon in order to make their robot more consistent. Not faster, but more consistent in terms of the amount of time that it takes them to escape from each location. That's the first challenge that I have them do. And the second challenge I have them do is I create a message made out of Morse code. And I have the students develop a program so that they have a vehicle drive over my Morse code on the ground, collecting light sensor data. And they're not allowed to see this message. It is what I call the hidden message. And all I do is I run the robot for them and I hand them back their robot and they have to interpret the data. So what I'm doing in my university classes is trying to use what can be perceived by many as a toy to help them realize that it really doesn't matter what you're using. I find the Lego to just be very simple and easy for the students to be able to obtain this information. But it's a way for them to have real data and to analyze that data. And so however you're collecting that data, this is a really simplistic way to have them learn about reading data, plotting data, and translating the data. And so we go, the next step beyond that is while they read the data off of their plot and they're able to translate what the hidden message is, the next step is for me to ask them, all right, how would you automate this process? What was it that helped you translate that code? What were the things that you needed? And what I'm doing by asking them this question is not only helping them understand how programming works better, realizing what variables you need and the information you need in order to be successful, but I'm helping them to just realize that understanding and collecting data and interpreting data is an extremely important component of engineering. The final thing that I just want to talk about is that, again, engineering, I think, gets sort of pigeonholed as being the application of science. And so a lot of what we think about, or a lot of what the general public thinks is engineering, is really engineering science. And so there is this component of design that is extremely important to what I teach, as well as to what engineering is as a whole. And so I think you're seeing more and more in the United States the engineering that is being embedded into the younger levels is actually around design. And so I just want to talk a little bit about how to approach design problems within engineering to help students fully get an understanding of what engineering really is. And so for me, the first point is to make these projects, these design projects, these open-ended projects personally meaningful for the students. So as I mentioned before, getting a ball from point A to point B may not be very personally meaningful to a student, but perhaps finding a way for their younger sibling to be able to learn how to ride a bike, or maybe it's they're very interested in a certain sport, and so embedding a task that ties back to the sport that they're interested in. Making it something that interests them is extremely, extremely important in order to help students grab hold and be interested in what it is that you're trying to teach them. And so what I found is that the Lego tool can be a great instrument in order to have students be able to address some of the things that they're really interested in with something that they're at least slightly familiar with. It has to be something that's real world. It really can't be something made up. Now, it's not to say that there can't be some components that aren't quite real. I have a colleague who does something called alien design, where he has students develop things for students who are from a different world who are now going to be university students. And so they have different core body temperatures, they have different sleep schedules. But what that's doing is that it's tying it back to something that's personally meaningful to his students, which are the fact that they are students themselves and wanting to help improve the lives of fellow students. So while the aliens may not be real, it is something that can be real for them. And what I've said is that in some of the projects we do with clients who are in Kenya and Bolivia and Nicaragua, those individuals for my students are basically like aliens. They don't know what it's like to live in these various places. And so it's a great opportunity for students to have something that can be meaningful to them, even though there may be some components that aren't real life. And then, of course, there's this additional component that I just wanted to bring up because it's personally meaningful for me, is that once you have these students go through this process and make sure that it's hard to, as an instructor, to not present engineering design as linear because of the time constraints that we have within class. Make sure that students understand this is an iterative process and that they need to take a step back at some point and think about what it is that they've just learned. How do all these things that they're learning about the various different subjects that they're learning in school connect? And the best way to do that is to afford students the opportunity to reflect on what it is that they just learned. And how is it that it's really an opportunity for them to critically think about what they just did. How did they go about solving that problem? What sort of skills did they develop in terms of problem solving? What did they learn about people and users? Have they developed an understanding that engineering really requires a skill of having empathy for others, understanding the impacts on the environment, on a culture, on the economy? So there's lots of different things that students need to understand about engineering, and it really takes an opportunity for students to take a step back and think about what it is they just did in order to better understand what engineering is all about. And I think those sorts of opportunities are really going to help students expand their knowledge of what this field is, and that's what's going to increase interest and recruitment and retention in the field of engineering. So as we try to work on some of these aspects of embedding engineering into the younger classes and increasing that interest of students, both doing this in informal and formal settings, and preparing students for what the real world is, what it actually means to be an engineer and to engineer something and to have the knowledge of an engineer, whether you become an engineer or something else. What they really need to understand is that knowledge, there comes along this sort of civic responsibility, this understanding that we're not just preparing people to be the individuals who create the next big technology. We're also trying to prepare students to address the grand challenges that exist within this world. How do we maintain the planet? How do we get clean water and food for everyone, better health, and then, of course, safety overall. So I hope that this video was interesting and sparks conversations. And again, I apologize for not being able to actually be there in person. And I hope the conference goes well. And please don't hesitate to send me any questions you may have or any additional thoughts that you may have revolving around what I talked about in this video. Have a good conference.